All right, in this video, we're going to be moving on into section 1.7, and we're going to talk a little bit about linear independence and also its opposite, which is linear dependence during this video. So first thing I want to do is I want to do a couple basic definitions about what these are and how we're going to go about finding them. So if we have a set of vectors, let's say v1 through vp, so you can have as many vectors as you need, and they all exist in the same dimension Rn, then we can say that they are all linearly independent if the vector equation x1 v1 plus x2 v2 plus dot 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 equals the zero vector has only the trivial solution. So if the trivial solution, which from the last video says that x must be the zero vector, if that is the only thing true, then the set of vectors you use to create this vector equation will be linearly independent. Now you can probably guess the opposite of that. The same set of vectors, they are said to be linearly dependent if there exist weights C1 through CP that are not all zero, such that the homogeneous equation is true. So if you can find a set of constants that are not all zero, and they equal the zero vector by multiplying by the respective vectors, those are said to be linearly dependent. All right. So kind of putting all this formal jargon into a definition I have by the asterisk down here is if the columns of matrix A are linearly independent if and only if the equation AX equals 0 has only the trivial solution. What you might recall from the previous video in section 1.5 is the only way that you will have the trivial solution only is if when you set up your augmented matrix and you row reduce it, there will be no free variables. So if you don't find any free variables, then it has the trivial solution only, and thus the vectors are linearly independent. And then you guessed it, linearly dependent, kind of going the same idea. If there is a set of weights that exist, that means there are infinitely many of them because there must be one free variable at minimum. So remember with the homogeneous equation, there's either one answer only, which is the trivial, or there are infinitely many. You cannot find a no solution with this type of equation. So when you want to determine if vectors are linearly independent or dependent, the most basic way is to figure out the free variable idea. All right, so let's do an example to kind of talk through this. Let's assume we've got three vectors. V1 is the vector 1, 2, 3. V2 is the vector 4, 5, 6. And V3 is the vector 2, 1, 0. Question 1. Do these three vectors make up a linearly independent set? So it's going to be a yes or no question. And then if possible, find a linear dependence relation among V1, V2, and V3. So it's kind of a two-part question. You may not need to answer both parts here. First of all, let's do question 1. Do these three vectors form a linearly independent set? So remember, to do that, you need to set up the homogeneous matrix equation using the vectors in the problem. So to do that, we're going to set up an augmented matrix using the three vectors at the top as the columns of your matrix. And then to make it a homogeneous equation, remember your last column needs to be all zeros. So now the question for part A just becomes, it's a yes or no question. Are they linearly independent? So all you'll need to do is get this into echelon form in order to figure out if there's any free variables. So let's see if we can get this into echelon form. Focusing on column 1 here, I'm going to take row 2 and subtract 2 row 1s. And for row 3, I'm going to subtract 3 row 1s. So if I leave the first row alone, row 2 will become 0. 5 minus 8 is negative 3. 1 minus 4 is also negative 3, and then 0. For row 3, you'll get 0. 6 minus 12 is negative 6. 0 minus 6 is negative 6, and 0. Two things here, and I think we actually saw this at the very end of the last video. In this example, row 2 and row 3 are multiples of each other. You can multiply row 2 by 2 and you will have row 3. So remember, when that happens, you end up letting the most bottom of those rows become all zeros. So I'm going to let the bottom row become all zeros. And we also can notice that if we were to take row 2 and multiply every element by negative 1/3, it would simplify it to an extent. So that would be 0, 1, 1, 0, 1, 4, 2, 0. And so that is our echelon form. That's as far as you need to go to answer the first question. You've got a pivot position in X1 and X2's column. There is no pivot position for X3, but you do have a row of all zeros. So remember, that tells us that X3 is a free variable, which implies that the set of vectors v1, v2, and v3 are linearly dependent. So remember, if you can find at least one free variable, that means there's infinitely many weights that work here. It has to be a linearly dependent set. So since they are linearly dependent, that actually allows us to answer the second question. Because if it is linearly dependent, you should be able to find a relationship among v1, v2, v3. In order to do that, you need to continue on with your echelon form and put this into reduced echelon form. So the only thing you have to do to get from echelon to reduced echelon here is get rid of that 4 in the top row. So I'm going to take row 1 and I'm going to subtract 4 row 2's, which will give me 1, 0, 2 minus 4 is negative 2, 0, and then everything else remains the same. Remember from the last video, we can write out what this is telling us. The first row is saying that x1 minus 2x3 must be 0. The second row is saying that x2 plus x3 must be 0. And as we already talked about in purple, x3 must be a free variable. Solve for your basic variable. So x1 will need to equal 2x3. X2 will need to equal negative x3, and x3 is a free variable. So when you're looking at the relationship, so it says find a linear dependence relation. Remember that there are infinitely many of these, so there's a bunch of right answers in this case. If you recall from the last video, what we did is we wrote our answer in parametric vector form. And so since x3 is our free variable, that means we're going to have one vector relation here. And if I use the coefficients from last video, we can see that we should be doing 2, -1, 1 as our vector. So what you're trying to do here is, if I go back to the previous slide, and I'll kind of write it here, you're trying to determine that vector x is equal to c1 v1 plus c2 v2 plus c3 v3. You want to plug in a set of 3 constants that make this statement true. So besides doing all zeros, because you don't want to do that because that's the trivial solution, let x3 be any number you want. Honestly, I'm going to be very simple here. I'm going to let x3 be 1, substitute that in, which doesn't really do anything, and then that gives me a relation for this problem. So we can actually say that the relation for vector x with v1 through v3 would be something along the lines of 2v1 minus v2 plus v3. So in this case, this would be your relation for your vector x in this case. Now, that's not the only correct answer. Remember, that's one of infinitely many correct answers in this case. So you don't want to use all zeros because we don't want to get in the habit of using the zero vector. While it's not wrong, it does lead to a bad situation as you move through the future sections. All right. So while finding a relation is great, and we're going to do that a good bit along in this class, sometimes we're going to work problems where we just need to know whether or not we have a linearly independent set of vectors. Because if you do, that allows you to do certain things. And if you don't, well, either you got to fix it or it doesn't allow you to do certain things. So here's our next example. Determine if the columns of this matrix form a linearly independent set. So if you were to think of the first column here as being V1, the second column being V2, and the third column being V3, are they linearly independent of each other? So we're going to set up our augmented matrix. Because remember, to check linearly independent, you're setting up the homogeneous equation in this case. So if I were to take my matrix, I'm going to take exactly what you see here. We'll switch it around in just a minute. All right. And then to make it homogeneous, I'm going to add the 0 vector onto the end. Now, once again, this is just a yes or no question. It's just asking, are they linearly independent, yes or no? And your job is just, in this case, to figure out, is there a free variable or not, which can be done from echelon form. So if I wanted to put this in echelon form, first thing I want to do is get that 1 into the upper left pivot position. It doesn't really matter what number you put up there, but we always like to put a 1 there if it's easy enough. So I'm going to interchange row 1 and row 4. So 1, -3, 2, 0. The two middle rows will stay the same. Then move this down, 0, -8, 5, 0. So I'm going to use that first pivot position to get rid of the 3 and the -1 below it. So I'm going to take row 2 and subtract 3 row 1s. And then I'm going to take row 3 and just add row 1. So that's going to give me 1, -3, 2, 0. For row 2, I'm going to end up getting 0. Let's see, that's -7 plus 9, which is 2. And then 4 minus 6 is -2, 0. For row 3, I'm going to add the top row to it. So that would be 0, 2, -2, 0, and then 0, -8, 5, 0. Now, you'll notice here, not only are two rows multiples of each other, you actually have two rows that are identical, and that's row 2 and row 3. So remember, when two rows are either multiples or identical of each other, the most bottom row is going to go to zeros. So I know that this row here, the third row, is going to go to all 0. And remember back to when we learned echelon form in section 1.2, when you have a row of all zeros, you want those to go to the bottom. So what I'm going to do now is I'm going to interchange row 3 and row 4, technically post turning that row to all zeros. So what I mean by that is your first row will remain the same. Your second row will remain the same. There's no need to scale it because remember, we don't need reduced echelon. Echelon will work fine. This green row that I have circled of all zeros, I'm going to go ahead and move that to the bottom. And then I'm going to move row 4 up. Now, at this point, I don't need to go any further. All right. Because at this point, I know that I have a pivot position in the X1 column. I have a pivot position in the X2 column. And eventually, I'm going to put a square around this one. You will get a pivot position where this 5 is here. The reason I know that is because since row 2 and row 3 at this point are not multiples of each other, that next row will not go to all zeros. So there's going to be a number there that if I eliminate the -8, some number is going to be in that 5 position. All right. So here is the trick to this now. All right. The question is, do the columns form a linearly independent set? When you look at this, I always have somebody say no because there is a free variable. But that is where this can get tricky. There is actually not a free variable in this problem. Because if you go back up to the original problem, there are 3 vectors. You're trying to figure out, is there a constant that goes in front of each one other than 0? Well, going based on pivot positions, you've got one for your x1, one for or your v1, one for your v2, and one for your v3. So you actually find a pivot position that coincides with each vector. So in this case, even though you have a row of all zeros, there are no free variables in this problem. So when the question asks, are the columns of this matrix a linearly independent set? The answer is yes, because there are no free variables. The reason you got a row of all zeros here is because you have more entries than vectors, which usually means that you're going to pick up extra terms that you don't need. That's why you pick up this row of all zeros. So I threw this in here to kind of get your mind out of the assumption that just because you get a row of all zeros does not mean you have a free variable. It's all about, do you have enough pivot positions to coincide with the respective vectors, or earlier in this class, variables you're trying to solve for. All right. So the last two examples were us actually doing row reduction to figure out if it's possible. The good news is that there are sometimes you will be able to do a shortcut to figure out whether a set of vectors are linearly independent or dependent. So in the book, they do a little section that's called linear dependence by observation. And there's 3 situations where this is going to play a role. So I'm going to go over all 3 with you, and then I'm going to show you an example of all 3 so you know what you're looking for in the future. Shortcut 1, we'll call it. A set of vectors v1 and v2 is linearly dependent if and only if v1 is a multiple of v2. They are linearly independent if neither of the vectors is a multiple of the other. So one of the big things about this one is it essentially says is if you have 2 vectors only, if they are multiples of each other, they are linearly dependent. If they are not multiples of each other, they are linearly independent. And it's that simple. But you can only use this rule if there are 2 vectors only. If you have more than 2 vectors, shortcut rule 1 will not work. We'll call it shortcut 2. If a set contains more vectors than there are entries in each vector, then the set is automatically linearly dependent. All right. So if you're thinking in dimension wise, if you have a set of p vectors and each of them has n entries, so there's n numbers down the vector, it will be linearly dependent if the number of vectors p is greater than the number of entries. So a simple example for that would be if you have 5 vectors, but each vector only has 4 entries in it. Immediately, without doing any work, I know that they're going to be linearly dependent at the end. And last but not least, we'll call it shortcut number 3. If a set of vectors, and it doesn't matter what dimension you're in, if you ever contain the 0 vector, if any of the vectors are the 0 vector, then your set is automatically linearly dependent. So from these shortcuts, the last 2 only show linearly dependent. All right. The only shortcut that allows you to show linear dependence would be if you have 2 vectors and you can look at the multiple idea. So make sure you keep that in mind as you're learning these shortcuts. All right, so went over 3 shortcuts. Let me go through one of each kind with you. So these are not problems we're going to work too much in detail here, but I just want you to kind of be aware of what you're looking for in this case. So matching these up with the rules from the previous slide. On part A, you've got 2 vectors. You have the vector 2, -4, 8, and the vector -3, 6, 12. Since there are only 2 vectors here, the fastest way to check this is, are they multiples of each other? And there's a few different ways people do this. You can think of a number that multiplies to get this, blah, 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 blah. Honestly, the fastest way I think to check multiples is to set up ratios from one vector to the other. So how I think of it is I take the first entry of each vector and I divide it. So 2 divided by -3. Then I take the second two numbers, -4/6, and I do this for each number in the vectors. And I make sure I always do the first vector over the second vector. You notice that I put equal signs between them because if they are multiples of each other, each of these ratios should be exactly the same. Now, when these simplify, you get -2/3, -2/3, +2/3. Unfortunately, while close, those are not the exact same numbers. So therefore, the two vectors are not multiples of each other, which means they are linearly independent. And that's how quick you can check them. But you can only do this shortcut if there are two vectors only. For rule B, or part B here, you have three vectors, 2, 1, 4, -1, and -2, 2. So what I notice about this is that there are three vectors, which remember that was our p-value from the previous slide. All right. And then you have two entries of each vector, which is the n value. And in this case, since the number of vectors is greater than the number of entries in each vector, I don't have to do any work. Immediately, these three vectors have to be linearly dependent of each other. And last but not least on this slide, part C, you've got three vectors, 1, 4, -7, -2, 5, 3, and 0, 0, 0. So the big talking point here is that the 0 vector is included. Immediately, if you see the 0 vector in a set of vectors, I know that those vectors, no matter how many there are going to be linearly dependent of each other. And so while these three shortcuts will not show up on every problem, if they do, you are more than welcome to use them as long as you label and explain your reasoning. If these three rules don't work, you have to refer back to the first way we did it, and you have to set up a augmented matrix as a homogeneous equation and then figure out if there are any free variables or not. All right, and then the last thing I want to do to finish up our linear independence versus dependence talk is bring back one of those critical thinking questions. So we haven't done one of these in a couple of slides or a couple of videos, so let's do another one. I want you to find every value of h for which these three vectors must be linearly dependent. All right, so force these vectors to be linearly dependent. Now, unfortunately, none of your three shortcuts are going to work. You've got more than two vectors, so you can't use the first one. There's not more vectors than entries because they equal, can't use that. And obviously, none of these are the 0 vector. So therefore, the only way you can check this for linear independence or dependence is to set up a homogeneous augmented matrix. And so we're going to do that. Down here below, I'm going to take our three vectors, 3, -6, 1, -6, 4, -3, 9, h3, and then I'm going to add the 0 vector on the end. We're going to try to reduce this as far as we can. I don't see anything that jumps out to me. You could interchange row 1 and row 3, it looks like, but I'm actually just going to leave them where they're at. I'm going to take row 1 and multiply it by a third, just so I don't have to interchange anything. So 1, -2, 3, 0, -6, 4, h 0, 1, -3, 3, 0. Now, if I go to eliminate everything below the first pivot position in the first column, I'm going to take row 2 and add 6 row 1s, and I'm going to take row 3 and I'm going to subtract row 1. So 1, -2, 3, 0. Row 2 is going to become 0. That is 4 minus 12, which is -8. Then you're going to have h plus 18 and then 0. And then for your last row, you're going to end up with 0. Negative 3 plus 2 is negative 1. And then you've got 3 minus, oh no, sorry, looked at the wrong row. Don't do that like I did. Then you'll have 3 minus 3, which is 0, and then 0. All right. So keep going. At this point, I tried to avoid it, but I'm going to have to do it anyways. We need to interchange row 2 and row 3. All right. And also while I'm doing that, so after I interchange these two rows, since the negative 1 is the only thing in that row that's going to be there, I really want to make it a positive 1. So then I'm going to take the new row 2 and apply the negative of it. And let me show you what I mean by that. The first row is staying the same. After I've now interchanged row 2 and row 3, I'm going to negate the new row 2 just so it becomes 0, 1, 0, 0, and then 0, negative 8, h plus 18, 0. Once again, on small steps like that, I have no problem with you doing that for your tests and stuff, but just make sure you label what you're doing. All right, so we're trying to go to reduced echelon form here. So I'm going to get rid of the negative 2 on top. So I'm going to take row 1 and add 2 row 2s. And I'm going to take row 3 and add 8 row 2s. So my middle row remains the same. My top row is going to become 1, 0, 3, 0. Not much changing there. And my bottom row becomes 0, 0, h plus 18, 0. So as you look at this, remember, you're trying to force this to be linearly dependent, which means you need to force a free variable here. So if you look at our problem, you've got a pivot position for x1 for the first vector, a pivot position for the second vector. Remember, if this ends up being a pivot position, the h plus 18, then you'll have no free variables and thus it will be linearly independent. So if you want to force this to be linearly dependent, you need to force this last row to be all zeros. That can simply be done by taking h plus 18, setting that equal to 0, and if you solve, h must be negative 18. That's the only way to force a row of all zeros and thus forcing x3 to be a free variable. So that ends the video for section 1.7, talks about linear independence versus dependence. Once again, a lot of the sections in chapter 1 are not very long. It's all about foundational stuff as we move through this first chapter.